Greetings, physicists. Today we're back with another lesson from our waves unit. We're going to talk specifically about light. Last time I was with you, we talked about the Doppler effect. Now we're going to talk about light waves and specifically how we can use the wave equation to understand light. And if you're following the Unit 5 waves curriculum, if you were back one at day 19, then perhaps you noticed that we talked about wavelength and how that allows you to identify different colors or why colors exist within light. So they talked about separating light into various colors based on its wavelength and the fact that certain light colors have longer wavelength and others have shorter, and a prism can help slow down waves at different rates, thus separating them so we can see the full spectrum of color in light. Now we're going to talk about possible mediums for light. The first thing I'm going to do is I'm going to define speed, frequency, wavelength, and period. And then we're going to jump over to the reference table to understand what we get from it in terms of understanding wavelength and frequency and the electromagnetic spectrum. So first I'm going to define these terms. Okay, so we've got speed, frequency, wavelength, and period. And so you're going to want to take these definitions down in your notes, all right? Perhaps you've looked at them before. Speed, of course you have if you've been in this physics course. And so I'm just going to define speed very simply, a little bit less technical than usual, and I'm going to say the rate at which something travels, all right? Usually we measure that in meters per second, so I'm going to put that at the end. You can measure it in miles per hour, you can measure it in other units as long as it's a distance over a time, all right? Now I'm going to go first to wavelength. And I'm gonna be very simple again. I'm just gonna say the length, the horizontal length of a wave's shape. Okay, and in parentheses, I'm gonna expand on that a little bit. That's actually, I'm gonna expand outside of the parentheses. I'm gonna say the horizontal length of a wave shape, specifically a single cycle of that shape before it repeats. Okay, and these definitions are going to make a lot more sense once I make a visual for you. Okay, which is the next thing I'm going to do. With frequency, I'm going to say the amount of waves that pass a given location over a set period of time. In other words, how frequently a wave oscillates, right? And you're seeing that I'm throwing some new terms at you, but I am going to define those terms as well. Okay. And let me make this graph before I go any farther, right? Because they're getting kind of in the weeds, and I want to make sure they understand what I'm laying down. Okay, so we have this graph here. I'm going to draw one crude cycle of a wave. Actually, I'll draw two cycles. Put this arrow to indicate that we're going to keep going, all right, in both of these directions, all right. This curve would continue to go, all right, and now I want to define some terms, all right. So first thing I'm going to do is visually define wavelength. So like I said, it's the horizontal length of a wave shape a single cycle of that shape before it repeats. And so from here to here, we could call that wavelength. Okay. And then assuming, let's say that this was all taking place over 1 second. Then we could say that the frequency, this curved f, would be 2 cycles per second. And the other thing that I want to point out, I'm just going to write SCC for second. The other thing that I want to point out is that you can see that possibly there is an inverse relationship between the frequency and the wavelength. So the bigger this wavelength would get, the fewer cycles that would happen in that second. I'm going to draw another curve to illustrate that. Very important that we understand this before we move forward. All right, so let's say that I had this new waveform apply on the same graph and it's twice as large. All right, so its wavelength, I'm going to use a different color to plot its wavelength. And that's going to be all the way from here. Let me use the arrow. It's going to be all the way from here to here. All right. So its wavelength doubles. And then you see that the green waveform, all right, the green waveform only covers 1 cycle per second. All right. I'm going to write that in green down at the bottom. Frequency is 1 cycle per second. All right, and so we can see as the wavelength grows larger, so we doubled the wavelength, we halved the frequency. All right, the last thing that I want to write actually before I write down that relationship is I do want to define period, which I forgot to define. All right, and so period is a measurement of time. And period is specifically the time it takes to make a cycle of a waveform. One cycle of a waveform, right? And so all three of these things are so clearly related, all right? And so I was making a measurement that allowed me to construct the frequency, and that measurement was the fact that there was 1 second passing, I guess, for 1 cycle of that green waveform. The blue waveform, on the other hand, its period would be ½ a second. All right. And now, given all this, I'm going to write the definition relating the 3 terms that we're talking about here that are new. I'm going to write that over here. And it's not relating the 3 new terms, it's relating speed, wavelength, and frequency, but it is our wave equation, all right? We can say that velocity equals frequency times lambda, and lambda is our Greek symbol for waves, all right? Give me 1 second. There we go. Velocity equals frequency times lambda, all right? I'm gonna E equals velocity in meters per second. F equals frequency. Units for that are called hertz, which are inverse seconds, you could say. And then finally, lambda. That's that Greek symbol. It looks kind of like, I don't know, it looks like like an animal or something like that. Like an upside down Y. That lambda is for wavelength. And that could be measured in meters. Okay. All right. And so we've got these relationships. Now what I want to do is make sure that you get these notes down. And then I just want to take a quick look at the periodic, or I'm talking about chemistry here. I want to take a quick look at the reference table so that we can suss out how to use it really quickly. So I'm going to clear this. We got a lot of good information here. And now we'll take a look at the reference table just to make sure that we understand the value and how to use it to understand waveforms a little bit better. And so this would be the page with the electromagnetic spectrum. And I'm going to zoom in. Let's talk a little bit about what we're seeing here. Okay, so frequently on the reference table, you have these kind of these multi-dimensional charts that give you a lot of information, but it's a little bit hard to kind of suss out what's happening here. So we've got several things plotted on here, and then we have another kind of like change in, you could say, our scale in order to understand visible light. So let's talk about the top first. Okay, if we look along the top, we have our wavelength in meters, and that is in a vacuum specifically, meaning that's in a space where air particles have been removed entirely, okay? And so we're talking about, in an ideal condition, how large the wavelength of these various types of waves are, okay? We see at the very small end, we have gamma rays, and at the very large end, we have different types of radio waves, all right? You may have heard before about radio waves bouncing off of things, bouncing off buildings, and like the connection being difficult to maintain. That is in part because they have such a broad wavelength. Okay, and so if we're tracking across the top, we see that wavelength goes from low to high up here. Okay, and so it's increasing across the top. However, if we look at the scale on the bottom, we have frequency, and that is going from high to low, and it's decreasing left to right. All right, so this is increasing. If we're looking in that direction, this is decreasing. If we're looking in that direction, sorry, left to right is what I mean. All right, meaning that, again, we see this inverse relationship. As wavelength gets bigger, frequency diminishes or grows smaller. All right, final thing that I want to point out here is that we have the visible light scale. Note that it's only taking up this tiny chunk. Let me change colors. Only taking up this tiny chunk right here in the middle. Okay, and so it takes up this tiny chunk, but we expand it because it's so important. We really we see a lot of utility in connections to the world in studying visible light in the physics course, okay? And so we've expanded that part out. So the scale is disrupted, and we get to see all of the main, like, kind of integral colors in the visible light spectrum, all right? Note again that we're going from left to right. As we go from left to right, wavelength is increasing, frequency is decreasing, okay? So violet has the shortest wavelengths and is the most frequent. Red has the longest wavelengths and the lowest frequency, all right? But notice also the difference between these numbers is rather small. Okay, they're all base 10 to the 14th, all right? So they're all within a certain range of each other. And you could say that violet, in terms of its frequency, it looks like it's roughly double that of red. Okay, and so if you're going back to answer questions about various waves, here's where you want to come. Finally, this is something that we'll get to in the following video, but you need to understand indices of something we call refraction. We haven't talked about refraction quite yet, but it is going to come up again. So for now, we've defined wavelength, period, frequency, and speed of light waves, all right? And discussed how to use the reference table and discuss the inverse relationship between frequency and wavelength. Hope this was helpful for you, and I will see you soon.